Hey guys, today we're looking at our notes for gas laws, so let's jump right into it. Alright, so these are just some general ideas of what we're seeing: a hot air balloon, soda spraying all over you, a nice fluffy baked cake. These are all examples of gases at work. So gases have a couple of different properties that we're going to look at. We have pressure, volume, the amount or the moles of that gas, and then the temperature of the gas itself. So looking at each of those briefly, pressure is defined as the force that the gas exerts on a given area of the container in which it is contained. The standard unit for pressure is pascals. We have other ways of looking at it as well. We have pounds per square inch, PSIs. But it's just basically how much it pushes against whatever it's contained in. So if it's in a container, or if it's in a jar, if it's in a tire, it's pressing out against the walls of the tire or the walls of the jar that it's sitting in. That's what pressure is. Some key units here at sea level. These are all standard pressures at sea level. So 101.325 kilopascals. We have also atmospheres. So it's literally defined as the pressure of our atmosphere, of Earth's atmosphere at sea level. And then the PSI, the pounds per square inch pressure at sea level, is 14.7 PSI. Volume, we know that that's just the amount of space that our gas takes up. Liters or cubic meters, so meters cubed or liters, are both standard units for our volume of gas. The amount, this is a little bit tricky. We don't really deal with this a whole lot. We're dealing mostly with pressure, volume, and temperature for our gas laws here. But the amount of moles, the amount of atoms in a gas takes up is a little bit tricky. We measure it in moles since we can't measure individual particles. So again, this is not something we'll usually deal with a whole lot of. It's mostly just pressure, volume, and temperature. So temperature, of course, that's the measurement of heat, how fast the particles are moving. We'll have a whole unit of heat towards the end of the school year. But gases are moving and bouncing off of each other, so the temperature is just the measure of how quickly they're moving and bouncing against each other. Temperature, obviously there's a couple of different ways that we can measure this. Fahrenheit is what we're used to doing here in America. That's our standard units here in America. Our SI units are degrees Celsius. So freezing is 32 degrees Fahrenheit, 0 degrees Celsius. And then we also have Kelvin. That's our other range. Zero Kelvin is absolute zero, so no movement of particles. So that's just a degrees Celsius shifted by 273. STP, so that's our standard temperature and pressure. When we're looking at things, our STP is 0 degrees Celsius at an atmosphere, or if we're going with another scientific unit, our Pascal or kilopascals, and our degrees Kelvin would be 273 degrees Kelvin and then 101.325 kilopascals. So our gas laws are how they relate to each other. How do they interact with each other? How do those properties change based on kind of how they are? So our first one here, Boyle's Law. Boyle's Law is looking at what happens when we hold temperature constant. So if our temperature is not changing, what happens to our other variables? And in this case, our pressure and our volume are inversely proportional, which means if we multiply them together, we have a constant rate, because one goes up, the other one goes down. It's named after Charles Boyle, who was a really, really smart dead dude from back in the 1600s. He realized that for the same amount of air at a constant temperature, so if we're maintaining constant values for amount of molecules and for the temperature that it's at, as pressure goes up, volume goes down. Or vice versa. If volume goes up, pressure would go down if we're keeping everything else the same. We saw this. Now, we'll see this more so in an activity that we're going to be doing early next week called the Cartesian diver. It's going to be really, really evident. We saw this a little bit in the candle in a jar demonstration from yesterday. That initial kind of withdrawal or drawing up of the water into the jar, the beaker is the word I was looking for. When that initial amount of oxygen was burned up and we had a little bit of volume change, that little bit of a decrease in the volume led to a decrease in the pressure on the inside, or increase in the pressure on the inside, which drew the water up. So that's what That's where we've seen Boyle's Law so far. Again, we'll see it much more prominently in our Cartesian diver next week. Our next one, Charles' Law. That is what we're looking at with pressure being constant. So Charles' Law is our first one that is a direct correlation, where as one goes up, the other one goes up. As one goes down, the other goes down. So he looked at, again, looking at if we kept pressure the same, what would happen? If we heat up a gas, it expands. If we cool it down, it contracts. We saw this with the cold balloon, where we took that balloon and I sprayed the liquid coldness on it, and it started to contract. As that temperature decreased, the volume decreased. And here's just a little background on him. It was from the 19th century. Again, looking at if we keep the pressure constant and we increase or decrease the temperature, it's going to increase or decrease the volume directly. Third and finally, Gay-Lussac's Law. Gay-Lussac, let's see, I have a background information on him further ahead. No, I don't. Okay. So that is what happens when we keep volume constant. So if we keep the amount of molecules and the volume of those molecules constant, we're looking at how pressure and temperature interact with each other. So for a closed system, if we increase the pressure, it's going to increase the temperature. It heats it up. If we're going to decrease the pressure, it cools it down. That's basically what Gay-Lussac's Law is. Again, those are a direct relationship. As you increase pressure, you increase temperature. As you decrease pressure, you decrease temperature. We saw this with the candle in the cup. That was the most prominent part of that one, kind of the end of it after that candle went out and the air inside started to cool down once the candle was out. That decrease in temperature led to a decrease in pressure. So that's what drew up all that water in there. So the pressure went down, so that's what allowed it to draw up that water. So just to summarize, I have a little note card, and again, I talked about this before, that I stole this from someone on TikTok. It's a PVT card, so I have a picture of it right there. It's super useful for us because on one side, it's got all three of our different gas laws. It's got Boyle's, Charles, and Gay-Lussac's Law, and we've got PVT on the front side. So the way that this works, if we're looking at one of these three variables, or one of these three equations, like let's just look at Boyle's Law. Boyle's Law right here in the middle. We're looking at that. That is our equation there. V1 P1 is equal to P2 V2. So in that one, we're keeping temperature constant. So if we go ahead and stab the part of Boyle's Law, that tells me that if I'm holding temperature constant, if I'm going to increase my pressure, my volume is going to decrease, because those two are inversely proportional to each other. So you can see if I'm going to increase the volume, if I'm keeping my temperature the same, my pressure is going to have to go down in order to keep those things balanced. Or if I use any other ones, like if I look at Charles' Law, if I go ahead and stab the part that has Charles' Law on it, that equation is V1 over T1 equal V2 over T2. So if I'm holding my pressure constant, so I'm stabbing the P part, my pressure stays the same. If I increase the temperature, it's going to increase the volume. If I cool that gas down, it's going to decrease the volume. It's going to contract, just like we saw in that cold balloon. So it's just a super useful note card, because we always want to have a spot where we have the equations anyway. So this is just a nice thing that tells us how those are going to relate to each other. If nothing else, it's a formula card, but it's got that nice added benefit of being able to say, all right, if I'm keeping one constant, if I'm using Gay-Lussac's Law, if I keep volume the same, as I increase the temperature, I'm increasing the pressure. If I decrease the pressure, if I let off a little bit, it's going to decrease the temperature. So kind of cool. That's all I got for you guys. So if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, as always, reach out and let me know. Otherwise, have a fantastic day, and I'll see you soon.